Hi guys, today I'd like to introduce you to videoblocks.com, a website that allows you to include sound effects for podcast or video background on your website. With video blocks, there is no reason for your creative needs to be compromised due to budget constraints. You get studio quality stock including HD footage, After Effects templates, motion backgrounds, and more for a fraction of the cost. Go to videoblocks.com and get exclusive discounts on millions of additional marketplace clips, where you save 40% and can use clips for commercial and personal projects. And if you go to videoblocks.com/expansion drive, you can start your 7-day trial. Welcome everybody to another episode of Data Science at Home. In this episode, I'm going to talk about data science and healthcare with Saman Sarraf, who is a machine learning engineer and expert in computer vision. I'm very excited about this episode because it will be about healthcare, which I'm really attached to, about saving lives, and of course about applied deep learning and artificial intelligence.
This is Data Science at Home, the podcast that makes machine learning and artificial intelligence easy for everyone. Here's your host, Francesco Gadaletta.
So, I'm very glad to have you here. Hi, Saman.
Hi, Francesco. Good, and thanks very much for having me today.
So, Saman is an algorithm engineer at Konica Minolta and a machine learning expert. So, let me start from the beginning. Saman, please introduce yourself to our listeners.
I'm currently a machine learning scientist and algorithm engineer at Konica Minolta R&D lab in Silicon Valley. And over the past 2 years, I've been working on object detection and handwriting project using various deep learning architectures. And also, I used to be the lab manager of the neurocognitive aging group at Rotman Research Institute at Baycrest Hospital, University of Toronto in Canada, where I had this chance to work on a variety of functional and structural brain imaging studies. Regarding my academic background, got 2 master's degree. My most master's is in electrical and computer engineering from McMaster University in Canada, which is currently, fortunately, within the top 30 universities in the world ranking in the clinical and preclinical healthcare category. My final project over there examined data classification and analysis on resting state functional magnetic resonance imaging data, including Alzheimer's and normal subjects.
Wow, this is really, really impressive. And indeed, I renew my feelings here. I'm super excited about this episode. So what exactly do you do at Konica Minolta?
Actually, Konica Minolta HLUS is the company's main R&D lab in the United States. Since I joined Konica Minolta in 2015, I've been collaborating with the security and the imaging tech division, which includes 12 people from different backgrounds, ranging from, let's say, machine learning, machine vision, software development, data science. And our division actually most of the time concentrates on pattern recognition and machine vision projects, such as object detection, like I said, and photographs or camera images, or handwriting and intelligent character recognition, or optical character recognition engines in order to implement new ideas or improve the company's core technology. As a machine learning scientist, I focused on these 2 projects, especially handwriting recognition engines, developing algorithms based on deep learning techniques like convolutional neural networks and recurrent neural networks. My day-to-day, or I would say my role, involves in rapid prototyping to explore the feasibility of the new solutions, and also semi-product development by providing interfaces and APIs to the software team for integration into potential products. I'm really enjoying actually my work at HLUS, as it gives me the freedom to conduct research and do some development. In addition, I give consultation on machine learning related projects that are run by other divisions at KM, or by the actually company's clients, and I do some consultation actually outside the company as well.
And so your position, your role is about doing some research, but also at the same time, some kind of implementation, providing some kind of implementation, I guess.
Exactly, that's the thing actually I've been doing in Konica Minolta. We performing actually research on novel technologies in order to improve the Konica Minolta's actually core technology, or try to let's say develop some algorithms based on new ideas, like I said, actually like deep learning for object detection and stuff. Yeah.
And well, we will speak about later about some of your practical, the practical side of your job. Of course, also tools that you guys or you personally prefer. But to start with, I would like to focus the conversation around if you guys are in a team of data scientists, or if there are kind of heterogeneous backgrounds. How does it work there?
I would say yes, if you consider the algorithm development team, a data science team, which is becoming more popular these days in Silicon Valley. So they're considering, or I would say actually they're converting all the algorithm development to and they call it actually data science team. So most team members have a solid background in either computer vision or machine learning. We have a few software engineers and testers as well to finalize the codes and testing. The algorithm team members have the capability to work actually with open source libraries for machine learning and image processing purposes that require for sure actually coding skills, for example, in C++ and Python. And interestingly, a few of us, including myself, have expertise and knowledge working with big data platforms such as PySpark, Spark, that I've used actually those platforms for some clustering and data preparation projects.
In that respect, Saman, what was the largest data set you have been working on, if you remember?
Oh yeah, actually we got million of actually handwriting and printed character samples, which every time actually our raw data or samples actually is over a couple of terabytes actually, and we have to pre-process actually those data, and we have to apply our pre-processing, image pre-processing and processing and machine learning to all those samples, and get the model, the trained model from the actually machine learning platform.
In your background skills, you have used quite a bit of computer vision, if I'm not wrong. Also, I've been looking at your academic papers. You have been using machine learning for image processing and image analysis. Now, my question is that a coincidence with the fact that Konica do imaging products?
That's a really good question, actually. Yeah, my academic background is mostly in machine learning, with applications in medical imaging and computer vision. Yeah, Konica Minolta is basically an imaging and printing company that has numerous projects in computer vision and image processing domains. Over the past decade, as machine learning methods have rapidly expanded into the industrial level, many companies, including KM, decided to replace their traditional software applications with cutting-edge products and technology based on machine learning algorithms. So a traditional object detection software application that was developed using pure image processing methods, for example, is now being replaced by novel algorithm developed using, for example, deep learning models. So companies in the Bay Area like Konica Minolta are always looking for applied machine learning experts who have computer vision background and who are able to solve the traditional questions with novel machine learning or deep learning methods. Yeah, I would say yes, that's actually perfect coincidence that I have machine learning background and image processing and vision background.
And how are you guys connected to the other teams at Konica? Is there any multidisciplinary environment in which data science, for instance, is married to traditional imaging or printing or any other industrial product at KM?
Yeah, like I said earlier, there are several divisions at KMHLUS that sometimes overlap on projects. For instance, We have a peer research group conducting research on novel technologies and informing other teams about new technologies through presentation or joint meetings. But as the nature of the entire lab is research and development, each group does research to improve and optimize the existing algorithms or develop new methods. Additionally, our engineers, our scientists are working on new ideas to develop brand new methodologies in imaging, in machine learning, but of course, limited to the company's scope. What I'm trying to say is our research is pretty much around KM products and core technology, and some divisions are speaking with each other in order to exchange the information once the projects overlapped.
Now, Saman, the main reason why we are having this episode today is because I fell for one of your papers that I found on the internet. Also, I think because the two of us, are connected by some weird academic connections. So one paper of yours that really caught my attention is titled Deep Learning-Based Pipeline to Recognize Alzheimer's Disease using fMRI data that you developed at the University of Toronto, if I'm not wrong. Now, first of all, why would you like to recognize a healthy brain from one affected by Alzheimer's disease?
Right. Let me provide some background on these chained publications, actually. So this conference paper you're referring to is one of my individual research interests that I worked on by myself, for sure, with coworkers, with personal funding. I presented this paper at IEEE Future Technology Conference, IEEE FTC in San Francisco in December 2016, and I won the best paper award for that paper.
And I'm not surprised.
Yeah, and a more complete version of that paper is now online, and we call that paper actually DeepAD or DeepAD, which is like an acronym for Deep Learning and Alzheimer's Disease. And that parent paper, it covers the classification of both functional and structural MRI Alzheimer data. So, and the reason, over the past, I would say, 10 to 15 years, the classification / prediction of Alzheimer's disease has received increasing attention from researchers and clinicians. And you ask why Alzheimer's? So I'd like to just mention a couple of relevant statistics. According to the Alzheimer's Association in 2016, over 5 million people were suffering from Alzheimer's in the United States. This brain disorder is the 6th leading cause of death in the country. In the same year, Alzheimer's and other diseases of dementia cost the nation over $236 billion US. So, any kind of early prediction of Alzheimer's disease in any format, from lab to imaging tests, will help us to save lives and reduce that cost. That's why every year various research groups all over the world, in Europe, in North America, in Asia, try to improve the methods of early prediction of Alzheimer's disease.
Wow, these numbers are just impressive. Only 10% would make already an impact that is extremely high in the field. Is there any pre-symptomatic feature that you could detect with the method that you describe in your paper?
That's a really good question as well. One of the difficulties with prediction, the early prediction of Alzheimer's that experts usually encounter is that Alzheimer's disease in the early stages is easily confused with the normal effects of aging. That's why actually the medical doctors don't want to tell, let's say, this guy has Alzheimer, so they are pretty much optimistic.
Mm-hmm. That could be very high false positive rate. That's what you mean.
Exactly, Francesco. And that's why actually the Alzheimer's disease, unfortunately, could not be recognized very well and accurately in very early stages. Although these brain problems are different, they have similar effects and signs in imaging data, especially in the early stage of disease, like I said. But actually, in the particular paper, the patient population I selected and the final results and accuracy I achieved showed that my methodology can distinguish between Alzheimer's disease and normal control without confusing Alzheimer's disease with normal effects of aging. I had another research project in progress, which is targeting data on mild cognitive impairment, or called MCI, which is the stage between normal control and Alzheimer's disease. I'm working on the model to classify the MCI category as well. The primary results have been very promising. However, to develop a mathematical or machine learning model that can predict the progress of Alzheimer's over time is very challenging, and I'm not so sure and if we can do it, or the researchers are not quite so sure if it can be done by using only imaging data.
Wow. So to recap, your method basically reduces drastically the false positive rate with respect to previous methods. But there are also some chances that data might be incomplete, so that imaging data only would not be enough to cover and therefore to detect or to select certain features that are related to the disorder. Am I right?
That's correct. That's correct. Yeah, that's correct.
And so, what other data are researchers considering to integrate with the imaging data?
Okay, when you go actually to, let's say, psychological or like psychiatry department of like different brain institutes, like let's say Rotman, so they are using actually lots of data from psychological tests like MMSE, or they are for sure considering the patient's demographic information, and they try to build a mathematical model at the same time using all those types of information. So demographic information of the patients, psychological test scores, and imaging data, and they build a model and they are trying to correlate those all information together and build a mathematical model which covers all aspects of the disease. So they are not only focused on imaging data. They're trying actually to get other information in order to predict the progress of Alzheimer's disease. Because imaging data is pretty much enough for actually, let's say this guy has actually diagnosed diagnosed with Alzheimer or not. But in order to predict the progress of the Alzheimer, you need for sure more information.
Right. So the image would be just a picture of at a certain time. So it's quite a static data with respect to something that gives more dynamic profile of the patient.
Absolutely, absolutely.
And I'm very curious, actually, how would you integrate such information in a deep learning context? Let me explain a second. If you have, let's assume we are dealing with deep learning. So we have imaging data, and therefore one image becomes like, a matrix that you feed the network. And so you have like this, let's say 200 by 400 pixel. I'm just making some numbers here. And you start feeding your network. Now, how would you integrate diverse data in a deep learning context?
That's a very good and tough question. So in deep learning, actually, we have for sure different topologies. We have convolutional neural networks. We have also a very powerful and famous architecture. We call it recurrent neural networks, or LSTM, with long short-term memory. So if I just focus on recurrent neural network and LSTM, this topology is very strong at time series processing and time series prediction and classification. It means that if we can find some approaches or some ways in order to convert our imaging data as well as other kind of data I mentioned before, let's say demographic information or psychological tests, If we can convert all those data to time series, we can for sure actually take advantage and profit the recurrent neural network topologies and this architecture. Also, some people and some research groups showed very successful cases of using convolution neural network on different types of data rather than actually imaging data. For example, in voice recognition, with some transformation, they converted the voice actually data, the sound actually data to kind of imaging data. Also, they converted the spectral data from different sensors to imaging data, and they applied their machine learning algorithm, including CNN, to those kind of data, and they got really high accuracy. For example, for voice recognition, I had a news that actually they could get around like 98% accuracy. Even they converted voice actually to image. Even and the same thing for the spectral analysis. They converted those type of data to imaging data and then used actually come. So we have so many choices, and that's all about data science, and that's all about playing with data and data engineering. You need to know your architecture, and you need to know how to play your data and convert your data in a meaningful way.
Yeah, that's actually what you are saying is so powerful, because I remember I personally implemented my detector for these podcast episodes, and to do that, I used exactly the same trick, which was converting sound into spectral images, and then therefore analyze these images with a convolutional neural network. So it's pretty much very, very similar to what you're saying, and indeed it's about transforming the problem into something that deep learning can understand.
Exactly.
Now, classifying a complex disease with clinical data has always been challenging due to the fact that it is very difficult to identify and select the strongest discriminative features, especially when these things have to be handcrafted by people who must have some kind of domain-specific knowledge. Now, what happened with deep learning, as you are basically saying, and as you wrote in your paper, is that there was kind of a lot of improvement, right? So it basically, deep learning, just as a methodology, it helped already, just by changing the method with respect to traditional machine learning, it already helped. Is that the case?
Yes or no, but let me answer your classical machine learning classification question in this way. So, like you said, in any pattern recognition problem, whether we are using medical imaging data or computer vision data like camera images, for example, we need to find the most discriminative actually features or a set of features with that characteristic. In the second step, we try different machine learning topologies to perform our classification and see which one works better. This is what was done for years and years before the advent of deep learning, right?
Mm-hmm.
In a classification or recognition task, researchers often look for features that are, at least in theory, shift invariant and scale invariant.
Okay.
And this is the beauty of using deep learning architectures such as convolutional neural networks, because the convolutional layers extract shift invariant and scale invariant features to some extent with the help of other layers in the network. So, on the other hand, neural networks have always been one of the best solutions for recognition and prediction, as long as the given network is trained by a sufficient number of samples. So, to summarize, the shift and scale invariant feature extraction capability and complicated neural network topology of deep learning make this tool very powerful, enabling us to solve most classification problems. And one more thing to wrap it up, we don't have to forget the massive pre-processing that we have to do against the data before using our deep learning architecture.
Absolutely. So now that you mentioned it, let's describe a bit this methodology. What type of data did you start from?
Uh, The initial idea for this paper was to classify Alzheimer's disease from normal control subjects who were 75 years old or older using their functional MRI data and deep learning architecture. So the initial data was fMRI and deep learning. So before explaining the details of the methodology, though, I'd like to explain functional MRI a little bit.
Go ahead.
fMRI is an MR-based imaging technique that captures, I would say, the functionality and functional activity of the brain through blood oxygen level dependent, or we call it bold signals. There are two types of fMRI data: task-based and resting state. And in my paper, actually, I used resting state fMRI data because, for a long while, I've been using resting state and did some research on it. In resting state data acquisition, no explicit task must be performed by patients during the scan.
So these patients are just immobilized. So they don't have to move while the machine is scanning their brain. That's what you mean?
Exactly. They're laying down the machine with open eyes, no explicit task, and we are scanning them in a resting state. And that's why they call those type of data acquisition resting state fMRI.
Okay. All right.
And I would like actually to mention that in MRI or structural MRI, we are collecting data about the brain structure and anatomy, not functionality. That's the difference between MRI and fMRI. Back to the question, though, I considered a couple of points as I was doing the literature review before starting my development. First, I noticed that almost no research group, it seemed at the time, was interested in using fMRI data to predict Alzheimer's with deep learning. I also noticed that not very high-end or complicated pre-processing was being conducted in the Alzheimer classification papers. People who know a little bit about fMRI know that massive pre-processing is required to prepare fMRI data.
But is that the reason why nobody was using at the time fMRI data?
Yes, pretty much that's the main reason. And the other thing is actually the neuroscientists and people working in actually brain institutes mostly come from actually psychological and psychiatric departments. They don't have actually like interdisciplinary, let's say, expertise in machine learning as well as, let's say, functional MRI data analysis. That's another actually, let's say, source of issue probably.
Right.
And in my paper, so as actually my background was in fMRI data, fMRI pre-processing pipeline and optimization, I performed a very aggressive pre-processing pipeline against the fMRI data, and I prepared my samples. And I would say that one of the reasons I was able to outdo all of the accuracy rates reported in the literature before and even after me was because of the aggressive pre-processing. For this, I'm very grateful to Rotman Research Institute at the University of Toronto, where I work with a specific group to optimize the fMRI pre-processing pipeline.
And how many samples are we talking about?
So in my fMRI data classification, I had around 800,000 samples. So samples mean actually images. And in my structural MRI data classification, I had around 100,000 samples.
Wow. So it's 800,000 fMRI. That's an impressive amount. I mean, what's the resolution of each of these images? If you remember.
Yes, after actually pre-processing, so you get a time series most of the time around 120 points, and the image size, the 3D image size is 54 by 45 and by 54. So you are getting actually 54 by 45 images, and times by 54 again, times by 120 for one subject. Okay.
It's
And I
great.
had, yeah, and I had, thanks to ADNI dataset, I would actually thank this guy as well, in the University of Southern California. The ADNI dataset actually is available for public actually application, but you need to apply and get approval. So in ADNI, we have so many actually Alzheimer objects, and we have so many actually normal control. I use so many objects, and after those conversion, 3D volume, 4D volume to actually 2D images for those numerous number of subjects, I got around 800,000 samples for fMRI.
It's an impressive amount. And speaking about the methodology, what neural network topology did you choose?
In this paper and the parent paper DeepAD, I used the two-layer convolutional neural networks that had a similar topology, similar to LeNet-5. Also in DeepAD, we utilized GoogleNet to classify Alzheimer's and normal control. This paper was, I think, the first paper in the literature to target 2 or 3 objectives simultaneously. I used the fMRI data to perform the classification by a fully deep learning based recognition pipeline. Before my work, some researchers used a specific type of deep learning architecture called autoencoder, only for feature extraction purposes, which is very, very popular at the moment actually in medical imaging data analysis right now for people who are doing classification.
They use it also for to select features, or like a PCA, nonlinear PCA, or?
They apply autoencoder, which is pretty much convolutional layers to data. They get hierarchical features. In the paper, actually, the experts published it like 2-3 years ago. They showed they can use all the features at the same time, but if you want, actually, you can apply your PCA in order to the dimensionality reduction.
Oh, I see. But when you say that the network, this is the first in the literature to target 2 or 3 objectives simultaneously, is it equivalent to what today they call multitask learning?
Yes, because actually you need to handle the type of data in multi-aspect. Actually, it's not just because actually you have, let's say, images and you can just feed into the framework. Yeah, is multitask actually learning, because you need to actually take care of pre-processing within a pipeline, and you need actually connect your pipeline to the pre-processing, precognition pipeline. And sometimes that I developed in DeepAD, you need a post classifier, because post classification comes into the market and comes to the actually game and stabilize your classification actually results. So the reason I would say that was pretty much the first paper at the time, because actually people, like I said, before me, they use autoencoder only for feature extraction, and they applied their shallow learning, like support vector machine SVM, in order to perform the classification. But I pre-processed the data, and I used actually the deep learning LeNet-5 and GoogleNet for classification tags. So there was no explicit feature extraction was performed in my paper.
Oh, I see. And speaking about accuracy, what's the accuracy that can be reached with this approach?
Okay, in the paper, actually, we are referring to the accuracy I got from fMRI data was 97% in a slice level. In the bigger paper, DeepAD, we improved our accuracy pre-processing and data conversion and added with more samples, and we got an accuracy of 99.99% for fMRI data at the slice level from LeNet architecture, and almost full accuracy from GoogleNet. But actually, I got feedback from some scientists and researchers, and they were very interested in seeing actually what kind of accuracy we are getting from subject level. So I performed the classification on subject level data classification as well, and the accuracy rate reached 94.32 for LowNet and 94.24 from GoogleNet actually. In DeepAD, we used structural MRI data followed by an appropriate pre-processing pipeline for fMRI, and we slightly modified the data conversion methodology. And in the slice level, we achieved 98.79% from LowNet and 98.88% from GoogleNet, and an average accuracy rate of 97.88 in subject level from fMRI data on LowNet and 98.67 from GoogleNet. This is beyond the scope of our time today, but we developed a post classifier for subject level classification that could improve the accuracy rate of the classification for most of the models to around 100% accuracy. So we could, thanks to that post classification, we could perfectly actually classify all our subjects.
So that's perfect classifier. So I'm gonna schedule our next episode only about this post classification, a post classifier approach, because this is really intriguing now.
That's my pleasure.
So, well, 99.99% for fMRI data at the slice level doesn't really leave, it smashes the previous results, right?
That's correct. That's correct. So the previous result was around actually 93, 94 and the slice level. And another research group actually simultaneous with me used a similar topology with 4-layer convolution neural net, and they could reach actually, let's say 96 or something. They couldn't even actually reach my first 97. And the reason, Francesco, like I said, machine learning is machine learning in medical imaging. Just let me actually focus on medical imaging and fMRI, MRI data. Mm-hmm. Requires you to perform an aggressive pre-processing against your data. Otherwise, if you just want to use actually any kind of topology, let's say complicated topologies, architecture, LowNet, ResNet, AlexNet, without any appropriate pre-processing, you get a very high accurate result, let's say 96, 95, but you are not actually targeting 99.91. Because this paper goes back to the last year. After that, so many research groups and young researchers contacted me, and I told them, actually, I detailed everything in the paper. And one of the research group in China, there was 2-3 young researchers in that group, actually replicated my papers and got the same results. And honestly, I was excited like them, because actually I saw that some people could replicate my work, and they followed the pre-processing that I mentioned in the paper. It's really important.
So that's the usual case, is garbage in, garbage out.
Yes.
Okay. So how much human intervention is in this type of methodology, and more generally in Alzheimer's disease prediction?
In general, there are two main methods for predicting Alzheimer's or the progress of the disease. We a little bit actually discussed it earlier. One is actually psychological testing, such as the mini-mental state examination, or MMSE scores, a sort of questionnaire that is filled out by patients and scored by experts. The second method is medical imaging. So for sure, the first one is much cheaper but requires more human intervention, whereas imaging is more expensive and only experts are involved in interpreting the test. What I developed in my paper can be delivered as a software application at some point, and minimal human decision making is required. Is all trained model. The software can receive the raw data and apply the necessary pre-processing, data conversion, and feed forward prediction steps to the data in order to identify whether the data are Alzheimer's disease or normal control.
So, from the numbers that we are speaking about here, we are basically very close to perfection, of provided there is, of course, a very good pre-processing, etc. Now, how far is this methodology from being considered a medical device?
To be 100% honest with you, we are far from a medical device in which we use deep learning. And the reason is because in the healthcare industry, whether we are talking about software or hardware, we need to get approval from various organizations, and that slows the process of commercialization. That's why, unfortunately, the biomedical and healthcare industries are always behind the information technology industry. In this particular case, I personally had a very hard time convincing experts in medical imaging, neuroscientists, that okay, this model is pretty much perfect, but the paper was much more understandable to machine learning folks and researchers. There has helped because my background is in biomedical engineering for a long while, and I see that there has always been resistance against new methods and software applications, especially software applications in healthcare, which might be understandable because we are dealing with human lives actually in healthcare industries. Anyway, I hope to one day see more collaboration between IT and biomedical experts.
Absolutely, and likewise. Off topic, do you think it's an ego problem? That's a tough one.
That's yeah. I don't want to challenge actually any people, but I would say yes, yeah,
All
because
right.
actually yeah, the medical imaging experts or the neuroscientists when see actually a trained model that it can do the job like them or even better, for sure.
Yeah.
Actually, they see some let's say uncertainty about the let's say future work.
That's the major resistance that goes a bit across domain. So don't worry about that.
Yeah.
Now, do you think there will ever be the perfect detector anytime soon? And I'm not just talking about Alzheimer's disease. I'm just saying in general.
Um, Regarding actually machine learning models and that capability, I don't think actually there will be a perfect recognition system soon or anytime for that matter. There is always a chance that a machine learning method may fail when faced with new data. Even actually my pretty much perfect model, I used a huge amount of data, and I think actually that is the one of the biggest Alzheimer data set in the world. Even I used that actually data set and I trained a model. There is a chance to fail if I face actually new model. That's why I'm saying if you perform the aggressive pre-processing, you try actually, let's say, to make all the samples correlated a little bit and then perform recognition. Actually, we have the same scenario with medical doctors. When a machine learning method and model may fail, medical doctors or human beings, they make mistake too, like everybody. But
Absolutely.
but what is promising, at least to me, is to see that deep learning based models are much better at generalization and their failure rates are much slower. This makes the new recognition systems more reliable. Regarding, let's say, other brain disorders, honestly, some researchers contacted me a few months back and they wanted to use the same methodology on autism and Parkinson data. We'll see how far they can go, but I'm suggesting to all young researchers that understand actually the problems before development, then select their models and approaches. Because, for example, for Parkinson's, we need to do some massive literature review if that's biomarkers or not. It's not really easy to say that. For example, Alzheimer is biomarker. Uh, just the last word about machine learning development. I believe machine learning is not just about feeding data into the model and getting a trained model back. It requires lots of effort to make sense of the data and the models as well.
Absolutely agree with you. I mean, a lot of people think that with deep learning specifically, they can just, plug in new data and magically something will happen. But actually, indeed, every problem is different. Now,
Yeah, that's sorry for interrupting. Yeah, I totally agree with you. That's correct. Unfortunately, even in industry, even in Silicon Valley, we see those peoples, and the worst thing is that they are not few.
absolutely. Well, let's try to please some of the listeners of Data Science at Home who apparently are data hackers and they play with tools, with software, with hardware almost every day. And so I'm absolutely sure that they would ask the same question. What are the tools that you usually work with in terms of software and hardware if you use specific hardware?
Uh, for sure. I usually use Python and C++ for coding purposes. It is very actually popular and let's say in my field, computer vision and machine learning. But to the respected listeners, I would say Python is a must for data science. And if I run a deep learning model, I need a GPU for sure. Otherwise, the training the model can take forever. For the papers actually we discussed, I used the Cafe framework, C++ version, and did some visualizations in Python. And honestly, everything was done on Amazon AWS Linux servers that had GPUs installed on them. And for some parts of the projects, I used the NVIDIA Digits framework, which is freely available, and which is a bit easier for young researchers who don't like coding, because it has a GUI to interact with users. So to wrap up, Python, C++, and for deep learning, GPU is a must.
Absolutely agree. Now, Saman, it's always the time to ask you the philosophical question. Where do you see data science in 10 years from today?
Uh, so yeah, I like actually philosophy. Yeah, I envision a very promising and bright future for data science and data scientists. Almost all IT-related companies in Silicon Valley have teams for algorithm development or data science that work on various types of data to make sense of data. There are so many startups, there are so many established companies in Silicon Valley and across the world that that actually are expanding their data science team right now. And honestly, those data scientists, they make huge money actually for their companies. And also big data platforms are getting more stable because they have more customers and they are getting more stable, and engineers and scientists are getting more comfortable working with the frameworks. So I would say data science will likely remain a very hot job in the next 5 to 10 years.
Yeah, it's we have to see that because I also believe that artificial intelligence, more deep learning techniques are kind of changing also the way we do data science. But yeah, I agree with you. Partially, maybe 5 to 10 years. I don't know if it's gonna be the exactly the same as today. What do you think about deep learning techniques? Like, how would you see them evolving in the future?
Uh, Let me tell you a quick story about my experience with machine learning, and then I'll explain the impact of deep learning. In 2007, I completed my first master's thesis using artificial neural networks to predict the release profiles of novel drug delivery systems. That was my first big machine learning project, so in 2007. At that time, ANN was very popular, pretty stable, and we had a good understanding of how to use the models, how to adjust the hyperparameters, and so on. After a few years, the support vector machines frameworks and the ideas actually came to the machine learning market, and their application expanded and codes were established. Then deep learning techniques became more popular 3, 4 years ago. All said and done, I would say that. Even I'm challenging some people, but don't worry. I believe deep learning can be considered a revolution in machine learning over the past 20 years. For example, convolutional neural networks, where it's more straightforward mathematics, solve recognition problems much more accurately. I've no doubt that we're going to hear more exciting news about deep learning methods and applications, and deep learning frameworks will become stable and easier to use and integrate into the software application in very, very close futures.
I see it coming, and I'm also. I mean, as only people who are actively involved with deep learning understand and would agree with you for sure. How about data science in 2018? Like, if let's try to be a bit myopic with respect to the future. What do you think data science will evolve? How do you think data science will evolve in the immediate future?
What I can tell you for sure is that we're gonna see growth in the number of companies with a data science department. So companies will be hiring more data scientists. There are certain important industries, including healthcare, that still need to become more involved with data science concepts and technologies. And I believe this can happen within a year or two, because I see so many papers and so many articles actually about the application of big data / data science in healthcare. And the data science is actually coming out of the research topics and going to the industry level. And I believe actually big data frameworks are providing more stable machine learning libraries and capabilities, and they are becoming easier and easier for data scientists in order to use in their actually projects. So I would say that actually data science is expanding too, for sure, in 2018.
And I also think that healthcare should become more involved with data science and probably overtake the ego problems, if any.
Yeah, just you know what, in accordance with what you are saying, I just want to send a message to the healthcare folks that break the ice, folks, and get the data science into industry.
Please do that.
Yes.
Saman, it was very nice to have you here. Very exciting podcast. I'm really glad to have you here at Data Science at Home. I truly enjoyed it. I'm sure that our listeners did too. I'm, of course, looking forward to seeing the progress with all your work, and also the progress that we expect on deep learning and healthcare. And, of course, good luck to you detecting diseases and saving lives.
Absolutely, absolutely. Thanks very much, Francesco, for having me today, and it was a pleasure to talk with you.
This episode is supported by Abe AI. The Abe AI platform joins advanced financial machine learning and natural language processing to give banks the ability to engage and support customers at scale using artificial intelligence. Visit abe.ai to see how we are changing the financial services industry, or how you can join our team. This was Data Science at Home, the podcast that makes machine learning and artificial intelligence easy for everyone. If you like the show, don't forget to write a review on Apple Podcasts, Stitcher, or Podbean. You can also find us on datascienceathome.com, where you can subscribe to our newsletter and get the latest updates. Thanks for listening. Hey, are you still there? Well, let me tell you about the newsletter of Data Science at Home. It's my free digest of the best content in artificial intelligence, data science, predictive analytics, and computer science. Subscribe now, datascienceathome.com.